We introduce CarcrashNet, the first open-source, high-fidelity dataset for full car crash simulation. CarcrashNet combines large-scale, finite-element car crash simulations and a state-of-the-art neural solver for predicting structural deformation during impact. Car crash testing is essential for safety, but it is also slow, expensive, and destructive. Each test requires a physical car, extensive preparation, instrumentation, and specialized testing facilities. Because only a limited number of physical configurations can be tested, engineers rely heavily on numerical simulation to explore different car designs and impact conditions before committing to a physical prototype. Crash simulation is ultimately a safety problem, not only a computational one. In the United States alone, car crashes were associated with more than 36,000 deaths, 4.3 million injuries, and damage to 22 million cars in 2025. Total societal harm just in the US approached $1.3 trillion. High-fidelity, finite-element crash simulations have been widely used as an alternative to physical crash testing. Virtual crash simulation enables engineers to evaluate more designs, more impact conditions, and more structural configurations before physical testing. However, they remain computationally very expensive. This creates a strong need for validated datasets and fast neural circuit models that can support scalable virtual testing. CarcrashNet addresses this challenge in 3 parts. First, we release large-scale component-level and full car crash datasets in a machine learning-ready format. Second, we introduce CrashSolver, a hierarchical neural solver designed to predict complete car deformation over time that achieves state-of-the-art performance. We also train tabular surrogate models on the full dataset. Third, we develop and validate a fully open-source crash simulation workflow against commercial solvers and physical testing data. The first part of CarcrashNet contains more than 14,000 bumper beam pull impact simulations. We systematically vary the geometry, material properties, impact velocity, and pull position. The dataset provides a controlled environment for studying deformation, energy absorption, peak forces, and other crashworthiness quantities. Here, we show representative simulations from the bumper beam dataset. Capturing these different nonlinear responses is essential for training reliable surrogate models. We then move from individual components to complete car structures. The full car dataset contains 825 crash simulations across 3 industry-standard car models: Dodge Neon, Toyota Yaris, and Chevrolet Silverado. These models represent different car sizes, body architectures, and levels of structural complexity. Together, they allow us to study whether machine learning models can generalize across fundamentally different car designs. The 3 car models also contain very different internal structures. The Dodge Neon, Toyota Yaris, and Chevrolet Silverado also use different front support systems, lower rails, subframes, suspension components, and load paths. These components govern how impact forces are transferred through the car. This diversity makes the dataset significantly more challenging than simplified body-in-white or single-component crash benchmarks. Here, we compare representative low and high velocity impacts for all 3 cars. Each car responds differently because of its mass, geometry, stiffness distribution, and internal load paths. A successful circuit must therefore learn both the shared physics of impact and the car-specific structural response. For each car, we vary the impact velocity and structural parameters that govern the crash response. The dataset's simulations include complete temporal deformation sequences rather than only final scalar outputs. The result is a high-resolution dataset describing how every car node moves throughout the impact. A large dataset is only useful when the underlying simulation workflow is trustworthy. We therefore validate our framework against Ansys LS-DYNA, the industry-standard commercial crash solver. The difference in peak wall force is approximately 7.2%, while the wall force duration differs by only 2.6%. The difference in peak internal energy is just 0.5%. These results show strong solver-to-solver agreement across important crashworthiness quantities. The agreement is also visible in the predicted car deformation. Our approach and LS-DYNA produce highly similar global deformation patterns, structural collapse, and final car shapes. We additionally compare the simulations with available physical crash testing references. This validation provides a physically grounded foundation for using the released simulations to train and evaluate machine learning models. In this work, we introduce CrashSolver, a state-of-the-art hierarchical neural architecture for full car crash prediction. The input mesh is first decomposed into semantic car components, such as the body shell, suspension, lower rails, and front support. Shared local encoders learn the deformation behavior of individual components. A global component transformer captures long-range interactions across the car, while interface message passing models how forces and deformation propagate between connected parts. Finally, a temporal decoder predicts the complete nodal deformation sequence throughout the crash. We compare CrashSolver with FigConvNet, TransSolver, and GeoTransSolver on hidden test simulations. CrashSolver achieves the best overall accuracy across all 3 car datasets. For the Dodge Neon dataset with 25 hidden test cases, it reaches an RMSE of 32.7 mm versus 33.9 mm for the next best model. For the Toyota Yaris with 50 hidden cases, CrashSolver achieves state-of-the-art results with RMSE of 21.7 mm. For the more complex Chevrolet Silverado with 15 hidden test cases, CrashSolver achieves 61.5 mm compared with 79.2 mm for the next best model. The largest improvement appears on the most structurally complex cars, demonstrating the value of explicitly modeling semantic components and their interactions. CarcrashNet establishes a new foundation for data-driven structural crash simulation. We hope CarcrashNet enables reproducible research in structural mechanics, crashworthiness design, and trustworthy AI-driven virtual crash testing. So maybe the next breakthrough in vehicle safety doesn't have to start from scratch.